Hello! I'm just an absolute huge fan of questions of expressiveness. Given a particular language, what sorts of things can we express? In this series of videos, I want to talk about 4 expressiveness results. First, I want to talk about several different presentations of the primitive recursive functions. How a for I equals 1 to n loop is expressively equivalent to defining f of x plus 1 in terms of f of x. In both cases, we have loops, either explicit or in terms of recursive function calls, with an explicit upper bound on the number of times we loop. If you've ever, when debugging a program, added a variable to count the number of times you went around a while loop, or done a recursive function call so you could end the loop if you went around too many times, to keep the program from not halting at all, that's really the essence of primitive recursive functions. Second, I want to talk about the limitations of the expressiveness of primitive recursive functions. Primitive recursion can't capture our full notion of Turing computability. Third, I want to talk about how we can extend our various presentations of the primitive recursive functions to capture the full notion of Turing computability. And fourth, I want to talk about one last presentation of the primitive recursive functions, one that seems hopelessly limited compared to the usual definition, but using clever coding arguments, we'll see that it winds up being just as expressive. I stumbled on these things while researching a question that's been bothering me for quite some time. Why are computable functions called recursive functions? Why is the theory of computation called recursion theory? I know that recursion is a thing that happens when we do computation, but what is so fundamental about recursion to computation? So I hope that you'll join me for Primitive Recursive March. This is a bit of an experiment for me, taking a really long video and breaking it up into weekly parts. I'll be releasing one video each Saturday. This will keep the videos a reasonable length, and I for one enjoy having a video to look forward to each week, so I hope you'll enjoy that as well. Let me know your thoughts in the comments. Let's start with the primitive recursive functions. We'll define the primitive recursive functions recursively. These are functions on the natural numbers, and here when I say natural numbers, I'm including 0 in that. Any constant function is going to be primitive recursive. The successor function, the add 1 to a number function, is primitive recursive. Any function that takes in a bunch of inputs and just outputs a specific one of them is primitive recursive. So this includes the identity function, f of x equals x, but also projection functions, f of xy equals x and f of xy equals y, for instance. Any sort of composition of primitive recursive functions, and these are multi-array functions, so we can compose them together in lots of ways, like f of g of x, h of x, is going to be primitive recursive. And this is really just a pedantic way of saying that if we can define a function of many variables as an expression involving functions we already know are primitive recursive, applied to those variables, that function is also primitive recursive. And finally, if g and h are primitive recursive, we can construct by a process known as primitive recursion the function f, where f of 0 and some other stuff is just g of that other stuff, and f of x plus 1 and some other stuff is h of x, f of x and that other stuff, and that other stuff. That is, we're feeding into h everything it could want to determine f of x plus 1 in terms of f of x. H gets to know x, that is the step of the recursion that we're on. H gets to know the previous value of the recursion, and H gets all of the other inputs to f as well. And why is this called primitive recursion? Well, simple. There are lots of ways of defining a function recursively, defining a function in terms of other values of that function, and this is really the simplest one of them, where we define a function at 0, and then we define the function at x plus 1 in terms of the value of the function at x. Let's look at a really basic example, the addition function. To define it by primitive recursion, we need to first specify what to do if the first argument is 0. And of course, we just return y. It's important that this be some primitive recursive function of the remaining parameters. right? In our definition, we had g of, well, in this case, there's only one y. So it's going to be g of y, where g has to be a function that we've already shown is primitive recursive. But of course, the identity function is one of our basic primitive recursive functions, so we're okay. Next, we must specify what to do when we increase the first argument, how this new value is related to the arguments and the previous value of the function. We want to define add of x plus 1y in terms of add of xy. And again, this is very simple. Add of x plus 1y is just one more than add of xy. And I've written plus 1, but we're applying the successor function. And again, the successor function was one of our basic primitive recursive functions. It takes a bit of getting used to start thinking about functions like this. I remember having to make this transition when I was first learning Scheme, a dialect of Lisp. Lisp-like languages are really built for deep recursive function calls, and so they want you to program in this way. Here's a sample of what this function looks like in a Lisp-like pseudocode. It takes a while to learn how to read this, since function names go after the parentheses around their arguments, not before. But the idea is the same as what I've written out mathematically above. If x is 0, then return y, and otherwise recurse and add 1 to the result. If you're more used to imperative programming, here's what that looks like. Right? If we want to add two numbers together, we have two cases. We have the case where x equals 0, where we just return y, and otherwise we look at the previous value of the function, what happens if we input x minus 1, and store that value, and then just take the successor of that value. But imperative programming languages really aren't meant to be programmed in like that. Each time you call a function, the computer stores a little bit of overhead to remember how everything was before you called the subroutine, what the values of variables are, where you were in terms of executing code, things like that, so that when the execution finishes with the subroutine, it can come back and continue executing the outer function. This isn't a lot of overhead, but when you're calling functions inside functions, inside functions, inside functions, thousands deep, you have to remember the state of the world at each of those levels, and it can add up fairly substantially. So instead, if you want to loop in an imperative language, if you want to do something over and over again, imperative programmers usually prefer a for loop. In this loop, we start off with the return value at 1, and then for each value I between 1 and x, multiplying our return value by I. And my goal for this video is to give you an intuition for how we can translate basic programs written with these basic sorts of for loops into compositions of primitive recursions, to convince you that any program you can write with for I equals 1 to n loops is primitive recursive, that these two notions are expressively equivalent to each other. So whether we think of factorial in terms of recursion or a for loop, we're working our way through its table of values step by step with the same steps. In the first case, in order to calculate 5 factorial, we first need to calculate 4 factorial. And to do that, we need to calculate 3 factorial, and so on and so forth, until we get down to the base case of 0 factorial, which is 1, and then we can resolve our way back. 1 factorial is 1 times 0 factorial, 2 factorial is 2 times 1 factorial, and so on and so forth. In the case of a for loop, however, we're directly working through the table from top to bottom, starting at 1 and multiplying by x each step we take. And the for loop tells us to stop after 5 steps in order to calculate 5 factorial. It's the same series of steps to calculate 5 factorial, we're just thinking about them in a different order. Now, there's a tricky bit here. This doesn't actually show that factorial is primitive recursive because we're using multiplication, and I haven't yet shown that multiplication is primitive recursive yet. The definition of primitive recursion says you're only allowed to show that a function is primitive recursive using functions we've already shown to be primitive recursive. whether you're writing them by defining f of x in terms of f of x minus 1, or doing this for loop construction. But luckily, multiplication is primitive recursive, and we can see this either in terms of defining the function recursively or in terms of a for loop. Both these programs have forms we're allowed to have when showing something is primitive recursive, either using recursive function calls to define f of x in terms of f of x minus 1, or a for loop for I equals 1 to x inclusive. And you know how this goes. To multiply x and y together, just multiply x minus 1 and y, and then add y to the result. We're starting at 0 and taking x steps forward, and each time we take a step forward, we're adding y. And the question is just, do we want to think about this in terms of where we are after one step, in terms of where we are before that step, or do we want to think about this directly in terms of applying our step forward some number of times? And because we've already shown that addition is primitive recursive, everything's perfectly fine. Both of these programs demonstrate that multiplication is primitive recursive. But if you're not convinced, we can go back to the mathematical definition of what it means to be primitive recursive. Right? We define the value that we get when the first input to the function is 0, and then we define the value that we get when the first input is x plus 1 in terms of x, y, and the value that we get when the first input is x, the previous value of the function. Now, if you actually look back to the definition of primitive recursion, we specify that the recursive definition has to be of a very particular form. Mult of 0y needs to be specified as a primitive recursive function applied to y. So technically we shouldn't just write 0 here. We need to specify that this is the constant 0 function applied to y. And then when we define the product of x plus 1 and y, it needs to be some primitive recursive function applied to x, the previous value of our function, so the product of x and y, and y. And so technically you have to note that this h is the composition of the multivariable composition of the addition function, and a projection onto the second coordinate, grab the second input, and a projection onto the third coordinate, grab the third input. There are some benefits to talking about primitive recursive functions in this highly pedantic way, but for the most part we don't need to worry about that. So I'm just going to write my definitions more straightforwardly, and I'll link you down below to some resources where they get really pedantic about primitive recursive functions, so you can see what that looks like and what some of the benefits are of doing that. Using primitive recursive functions to define other primitive recursive functions corresponds to nesting our for loops. We can translate back and forth. If we have a primitive recursive function defined in terms of other primitive recursive functions, we can translate it into a single subroutine with nested for loops. And if we have a program with nested for loops, we can translate it back. Here's our definition of the factorial function in terms of the multiplication function. But we can expand this multiplication function out as a for loop in terms of the addition function. And we can expand that addition function out in terms of the primitive successor function. And again, we can always translate back. If we have a program that makes use of these basic kinds of for loops, but they're nested, we can view each loop as defining an intermediate function on the way to showing that the whole function is primitive recursive. One might wonder if we're allowed to use fancier for loops in our program without leaving the world of primitive recursive functions. Here I have a program where the upper bound on the loop is some function of x and not just x. Is this okay? Can we always figure out how to translate this sort of for loop into just a basic primitive recursive definition of the function? Well, the answer is yes. Suppose that we wanted to show that this program here, which calculates the factorial of the square of a number, is primitive recursive. Well, this is just our factorial function, but with the input replaced by x times x. So we can write this as just the factorial of x times x, which is a multivariable composition of functions that we've already shown to be primitive recursive. And using this sort of procedure, we can show that any basic for loop, where the upper bound is given by some primitive recursive function, is primitive recursive, because it's just a composition of the function that represents that upper bound, and the function where that upper bound is replaced by x. We still need to be a little bit strict about what sorts of for loops we're allowed in our programs without leaving the world of the primitive recursive functions. We can't, for instance, change the value of I or change the upper bound on our loop while the loop is executing. These could be used to change our loop from a bounded one to an infinite loop, and the whole point of primitive recursive functions is to prevent infinite loops. And anyway, it's not clear how we can translate those sorts of loops into these primitive recursions where we define f of x plus 1, the result of going around the loop x plus 1 times, in terms of f of x, the result of going around the loop x times. Now, technically, I've only shown you enough to be able to translate for loops where there's one variable, the return value, that gets updated each time we go through the loop. And most programs with for loops have many variables that get updated each loop. I'll show you in a little bit how to encode multiple numbers into a single number using primitive recursive functions, so we could store all those variables in one variable and update that one variable each time we go around the loop, and then use multivariable composition to extract the value we want and maybe do some post-processing. But first, let me show you that some other basic arithmetic operations are primitive recursive. If we want to show that exponentiation is primitive recursive, we technically have to show that the function f of xy equals y to the x is primitive recursive first. Our definition of what it means to be a primitive recursive function really only allows recursion over the first input, and there's no really good way of defining 3 to the x in terms of 2 to the x. But there is a good way of defining x cubed in terms of x squared. So we have to do this backwards, and then we'll flip things around. We first define our function f of x like this. Right, y to the 0 is 1, y to the x plus 1 is y to the x times y. And then we just define the exponentiation function to be f with the arguments reversed. And again, this is a multivariable composition involving the projection functions. But if we're just being casual about this whole thing, it will be easier to write this recursion here, and we'll just remember that it's shorthand for the sort of construction above, and it's a perfectly fine way to show that something is primitive recursive. Next, we want a predecessor function. Arithmetic with just natural numbers is a bit tricky since we're not allowed to go below 0, so it's standard practice to define the predecessor of 0 to be 0 and the predecessor of x plus 1 to be x. Note that this meets the definition of a primitive recursion. We're allowed to define the predecessor of x plus 1 in terms of x and the previous value of the function. We're just completely discarding the previous value of the function and just returning x. So even though we've restricted our attention to the natural numbers, we still oftentimes want to talk about subtraction. And we do that using a function called bonus. This is subtraction, but if the result would be negative, it returns 0 instead. It might be good practice working with primitive recursive functions to try to convince yourself why this construction works, to unpack the shorthand going on, and to convert all of the functions on this page to nested for loop notation. To write all of these functions using just for loops and the successor function. It seems like we're building up a pretty practical programming language here, but it's really only going to be useful if we can do conditionals. Of course, everything in this language is natural numbers, so let's just do the standard thing and let 1 represent true and 0 represent false. This cheap trick here, using the constant 0 and 1 functions, gives us a function that tells us if a number is 0. This might seem silly, but we can compose with our bonus function to create various inequalities. For other inequalities, just switch the order or add one as appropriate. And if you're clever, you can use this to create an isEqual function as well. And finally, once we have our booleans, we can use them to produce different outputs to functions. This ternary function here, so in C notation, you may have seen this as $::. In Lisp notation, Lisp focuses just on values and not commands, so this is just if. This ternary function uses the same cheat of completely ignoring the recursion that we did with the isZero function, and it returns the third argument if the first is false, and the second argument if the first is true. It takes a bit of practice to change the way you think about conditionals from under these conditions do these commands to under these conditions return this value. But importantly, you don't lose any expressiveness here, translating the way that you code. Anything that you could do with ifs, such as defining a function piecewise, you can do just with multivariable compositions of this ternary function instead. And we can even do some modular arithmetic conditionals. We can tell if a number is even or odd just by alternating back and forth between 0 and 1. I'll talk about what to do with other moduli much later on in this video series, but we can do those too. And it might be a fun challenge to try to figure out how to do those things in the meantime. One of the key things we'd like to do is be able to keep track of more than one natural number at a time. Remember that when we were thinking of our recursions as for loops, we were only really able to keep track of one number, the number corresponding to the output of our recursive function. And we were applying our for loop or applying our update function iteratively to that value. To simulate programs that keep track of more than one value in a for loop, we're going to need a function that can encode multiple natural numbers as a single natural number. These sorts of functions are called pairing functions, and there's lots of them that we could use. We can get a really simple one just by composing our addition and multiplication functions, where pair of xy equals x plus y squared plus x. Here's a table of values for this function. So for instance, we'll use the number 10 to represent the pair 1, 2. The important thing is that no number appears twice in this table. We always need to be able to uniquely extract the pair that we're trying to represent with any particular number. Oftentimes you'll want a pairing function that takes on all possible values, but for this application we don't need that. We're just going to stick with one of the simplest possible functions that will do the job. So this function allows us to take two numbers and encode them as a single number. But of course, it's no good encoding multiple numbers as a single number if we can't extract our original numbers when we want to use them. To do this, we're going to need an integer square root function. We define it recursively as follows. The square root of 0 is 0, of course, and then to calculate the square root of x plus 1 rounded down, it's probably going to be the same as the square root of x rounded down, unless x plus 1 is a perfect square. This term here is usually 0, unless x plus 1 is the next square, right? Our function applied to x squared gives us the current square that we're on. So our function plus 1 squared gives us the next square, and we're testing to see if x plus 1 is equal to that next square. And we'll need an excess over a square function. How much a particular x is than the previous perfect square, which we can get from our square root rounded down using the monus function. This subtraction with a dot over it is how we write the monus function. Subtraction, but if the result would be negative, return 0 instead. So going back to our pairing function, suppose you had some z equal to the pair of x and y. We can extract the left input, the x, just by calculating our current excess over a square. This is easy to see if you look at the formula for pair. z is just some square plus x. And so that x is not going to take us to or past the next square. And so that x is literally just the excess over a square of the overall pair. On the other hand, if we take the square root rounded down of this value of our z, that's just going to be x plus y. The adding x doesn't take us to or past the next square. And so the square root rounded down of z is x plus y, and so if we subtract our x value that we've already figured out a formula for, we'll get our y. And of course, if you want to encode more than two numbers, you can just pair them together in sequence, and then to extract values, you just apply appropriate compositions of our extract the left and extract the right functions. So let's look at how we might translate a function that has two variables that get modified in a for loop using our pairing functions. Here I'm looking at a Fibonacci helper function that returns the nth consecutive pair of Fibonacci numbers. Each step of the for loop, we're going to step forward which pair we're looking at. Specifically, we'll let p be a variable representing the first pair, and then to update p, we'll simply use our left and right functions to extract the components of the current pair and use them to calculate the components of the new pair and then pair the results together. And so we're able to, with this code here, keep track of two numbers each step we go through the for loop, even though we're only updating one variable. And now this is of the form of some program that we can translate into a primitive recursive definition of a function in terms of other functions that we've already shown are primitive recursive. And so therefore this function is also primitive recursive. And then of course, if you want to extract an actual Fibonacci number from this, you just compose, you take either the right or the left of the output to this function, right? The output of this function is the encoded pair of two consecutive Fibonacci numbers. And so you need to extract one of those values depending on which one you want. So all in all, we can translate any program that calculates functions on the natural numbers that makes use of only the following features. The big thing we have is bounded loops. Loops where we know from the start an upper bound on the number of times we're going to go around the loop. And this can be given by the value of some variable or some expression. As we've seen, we can simulate having an arbitrary number of variable assignments inside these loops by tupling those variables together. And of course, we can nest these loops. That's the same as defining one function by primitive recursion in terms of another function given by primitive recursion. We also have all the basic natural number arithmetic we could hope for. Addition, bonus, multiplication, exponents, and we can do an inverse on multiplication to get integer division as well. I'll give a specific recipe for doing integer division in a much later video, or you can just figure that out on your own in the meantime. We have conditionals based on inequalities, and we can nest them to create conditionals on booleans on inequalities. We can jump out of loops early using conditionals. We just have a boolean keep track of whether we've quote-unquote jumped out of the loop, and then in each phase of the loop, check that boolean, and if it's true, don't change the current value that we're keeping track of. So we would still go through the loop the number of times that we promised that we would go through the loop, but just after we say that we've quit out of the loop, we just don't update anything anymore. And finally, it's perfectly fine in our quote-unquote programming language to use subroutines to make our notation cleaner, just as long as we're careful that our subroutines don't call themselves. Again, we're not allowed to have that sort of recursion. And this makes for a pretty robust programming language. Pretty much the only thing we're missing is arbitrary loops, loops where we don't have in advance an upper bound on their length. And yet, this limitation is enough to keep us from being Turing complete. There are computable functions that aren't primitive recursive, and in the next video, I'll show you some examples. So thanks for watching. Let me know if you have any questions or comments below, and be kind to each other.